Okay, so welcome back. So let me first remind you that I have posted the homework 6, but I want to show you the homework 6. It's related to the final presentation. So the first one is for you to engage in your group discussion and to come up with agree on a topic. And then you're going to, according to this topic or the paper, that you would create a rough sketch of the outline of your presentation. For example, I listed here, maybe I want to present the topic entanglement catalysis, and the paper is this one. I'm going to talk about some background on entanglement, and maybe nuisance measurization, give some examples, and maybe I mention some consequences, and then explain that in slightly more detail, and then conclude. So this is the homework for you to discuss with your teammates, and you're all going to present the same answer in your homework, but also post that in our discussion board in Blackboard. Okay. You have any question on the final presentation? Maybe this is a good time for you to ask questions.
I have a question.
Yes.
So we have 3 members in each group, and each of us gonna present like certain amount of time, or one of us are chosen and
It's up
presenting.
to the group. You could take turns presenting certain slides and order and etc., or one person maybe take charge of the presentation. I would like to see involvement from all the group members, but I don't want to set a strict rule. Okay.
Okay.
But
Thank you.
if multiple members want to present, then one person has to control the slideshow.
Okay, I see.
Okay, but it's not that technical issue, so it should be easy.
Okay, thank you.
Yeah. Okay. Regarding this homework, there are 2 more problems just for you to refresh. For example, the adiabatic evolution that we talk about, and then some entanglement, Schmidt decomposition, PVT criteria, etc. Okay, but that I think the most important is this one. You should start talking to your group members, because it's going to due in 2 weeks, and you should have answers before the night of submission. Okay, and this is just for you to decide a common paper topic, and then you will spend 2 more weeks to prepare for that presentation. Okay, so let me. Yes.
I had a question.
Yeah.
Regarding this template that we're supposed to complete, should all group members have the same template answers and just paste it on?
No,
or we have our own?
Well, you would set some temporary presentation title, and you give the key reference. It could be more than one, but there should be one key reference. Then this is just a usual presentation, a PowerPoint presentation or keynote. And yeah, just to sketch what you are going to do. I mean, you can finalize the detail later, but I just want to see that you already are engaged in the discussion. Does that answer your question? Okay.
How much time how long is
Can you speak louder?
How long is the presentation?
20 minutes. So yeah, so that'll be 20 minutes plus 5-minute question. So let me go back to the slides. Yeah. Yeah, so it's set here. So we have 7 groups, so we cannot fit in all the 7 groups in 2 days, because if each group would use 25 minutes, the 3 group would already take 75, and our lecture only has 80 minutes. So this is how I'm going to split. Yeah, so initially I want to just use the group number as the order, group 1, group 2. Was supposed to be group 3, but I made adjustment because there seemed to be one of the students may not be available for the group 3. So I would that the group 3 have more time. I think this group was going to only have 2 students in the end, but all other groups have 3 students. Okay, so and you have this assignment in the Blackboard. You can check out the list, but it's here, so you can identify yourself in which group and your group members. Okay, and you can set up discussions in the Blackboard. I already have discussion boards for each group, and you should also maybe set up separate meetings to discuss the detail. Okay, so I aim to have the presentation right after the Thanksgiving break, and so there will be 3 days of presentation, and December 7th is the last day of class. So we're going to have one presentation, or unless if there's anything goes wrong in the first day, then we can push the group to the other slot, and at least there's a one day that has some time to accommodate maybe some use of time here. Okay, any question on this? So I'm sure you already started the discussion, at least in the Blackboard, because that's the homework 1 of the first problem of homework 5. Okay, and I think homework 6 is the last homework. I don't plan to have any homework, or if I may give homework problem, those would be optionals. But this will be the last homework. But I want you to focus more on the presentation. Okay. Any more questions? Yeah, so let me go back. Yeah, so yeah, if there's no other question on the homework and final presentation, then today I'm going to discuss the topic of quantum data compression. This would allow us to understand the entanglement dilution. Then I'll move on to week 10's topic. It's about cloning in quantum mechanics and what the implication of no cloning means. Okay. Yeah. So to talk about data compression, I need to mention Shannon entropy. We have seen the expression of for Neumann entropy of a density matrix. Right? We've seen this trace rho log rho, but this in fact is a summation of lambda log lambda, and the set of lambdas are eigenvalues of rho, and they add up to 1. They are non-negative, so they represented a probability distribution. So this expression here is in fact called Shannon entropy. Okay, so usually you would say there's a variable x that appear according to probability distribution, px, in more of the classical terminology that people use in information theory. This is the same, it's just I'm replacing lambda k by px, okay? And the meaning of this Shannon entropy is that this is the average number of bits. We're using base 2 for log. So this is the average number of bits that are needed to represent a symbol x. Okay, this symbol can be from certain set with some distribution. Okay, for example, it could be the alphabet in English, or for example, I show 4 symbols A, B, C, D, they appear with this probability distribution. PA is 1/2, PB is quarter, PC and PD are all 1/8. Okay. So we can ask the question, if we want to encode encode messages with only 4 symbol, what are the average number of bits we need to use? So the Shannon entropy sets the lower bound. So you need to use at least, you can use more, but if you use the every number of bits fewer than Shannon entropy, then the compression would have a lot of loss. So you will not necessarily be able to recover your messages. Okay, but for this particular example, it's really interesting because you see that if I use 0, like binary 0 and 1, 0 to represent A, and only use 1 bit for A, because this appear with a larger probability, so I don't want to use too many bits to represent that. So in order for B, I use 1, 0. For C, I use 1, 1, 0. For D, I use 1, 1, 1. And you can calculate the average bits. First, you have to convince that this is a good encoding. After you have done that, then you calculate the average number of bits. 1 bit for A with probably 1/2, 2 bits for B with a quarter, 3 bits for C and D. They each appear with 1/8. And this is 7/4. In this particular case, it's the same as Shannon entropy if you calculate that. Okay, so that's the meaning of Shannon entropy, and this is one example of that kind of encoding.
Is it classical bits?
This is a classical bit. So I have, yeah, so Shannon entropy here is so classical, nothing quantum here. Okay.
So where does the probability come
probability is that they appear, right? So like English word, maybe A appear with some probability, right? B appear with some probability.
Okay.
Okay, but these are not necessarily independent. So, but English word may have specific correlation among words. For example, S and T would come together very often. Yeah, so it's not really necessarily independent for each other. Okay. But so that's the example I'm using. So I give you one more slide detail. So first, I ask you the question, what is this binary string encode? What message really is this? Can you maybe take 30 seconds to think about that?
Okay.
Yeah, so while I am going to maybe give you hints here and change.
Which direction should we encode this?
To the right, right?
Okay, okay.
And you will see that it's not really trivial in the sense that I could also ask myself, could I encode using maybe A as 0 and B as 0, 1, C as maybe just 1, 0, D as 1, 1. Could I do this? Yeah, and just by looking at it, you would immediately see that, no, this is not possible. Because if I give you this string, this bit string, I'm not telling you where you should break, right? I didn't tell you how you break the encoding, right? How do you put the command or to decode, right? If I use 0, 0, 1, should I assign this as A and this is also as A? Or should I assign this as A and this is B? So there's ambiguity, right? So it's not that arbitrary that you can just encode messages. So in this particular example, I'm sure there's already 1 minute passed. you will be able to decipher what this is. So let's do it together. I have ones, I start with 1. So it must be B or D or C, right? It must be this, but I look at the string, it's 1, 1, 1. So I must assign this uniquely to D. Does that make sense? And then I look at the next is 0, but there are 2 0. Is there 2 0? There's no 2 0. So this must mean individually it's a. Then I have 1 0. And I look up, there's 1 0, there's unique 1 0. So I must assign this as B. And then the next is 0. 0 or 0, 1. Is there a 0, 1? There's no. Uniquely is 0, right? Then the next one is 1 0. There's no 1 1 0 1, right? But here's 1 0. So I can uniquely determine that this is B. And the next one will be 1 1 0. So I can interpret that as uniquely as C, and this last 0 is A. Okay. So that should be the answer. Okay. Do you all get it right? So this shows that the encoding is not that trivial. Okay. But I think this is also the principle that that is used in the packages that compress files. Okay. But Shannon entropy set the lowest bound that you can encode using these bits. Okay. So, and we have assumed there's no error. Okay. If there's a flip of error, then there may be a situation that you have to consider how you decode. Assuming we're considering noiseless case, when you transmit information, there's nothing lost. Okay, so we're going to consider this idealized scenario, and I will mention the noisy case, but we're going to focus on this noiseless channel first. Yeah, so they call this noiseless channel coding theorem. Okay, so it's assuming that we're going to transmit information and the channel has no noise. Okay, but then there's a source that emit these bit or variables. Okay, so we'll consider a source which consists a sequence of random variable x1, x2, etc. This is the symbolic symbols for the random variable, and the values are usually indicated by a lowercase x1, x2, etc. And they're drawn from alphabet and a set of alphabet, for example, the ABCD that we use in the previous example to represent the output of the source. Okay. So, and there's also assumption, which may not necessarily hold in practical situation. There should be more that need to be added to modify this. But we're going to assume different uses of the source are independent, like A, B, C, D. These are identical distributed. So x1, x2, they follow the same. Basically, they follow the same distribution. They're not correlated, but they follow the distribution. So, for example, the appearance of A obeys some probability. B also obeys some probability. The existence of A doesn't change the existence of B, so they are not correlated. So this does not apply to the English alphabet, but we're going to just discuss this the simplest scenario. And just as an illustrated example, we're going to consider binary, so just 0 and 1, right? So each variable x, so the source may emitting a sequence of x1, x2, up to xn, assuming it's binary, 0 or 1, and 0 appear with probability p, 1 with probability 1 minus p. So if we have a sequence of this, we can divide any of the sequence into 2 types. So it's very useful to consider that. One is called typical. And what does that mean? Typical are those sequences that appear with high probability. So that, okay, that's a should reflect what typical means. But to be more mathematically precise, this means that for high probability, I mean that if you have large number of n, if n, this sequence is long enough, any of these typical sequences would contain roughly a fraction of p, which is 0, and a fraction of 1 minus p, which is 1. So for example, it could be 0, 1, 0, 1, 1, etc. But if you count number of 0, it would appear with probability p, and number 1 would be 1 minus p, 1 minus p. So basically, typical sequences are in the set of like permuting such a binary bit. Okay. And the other type, a typical sequence, is those that appear rarely. So meaning that they don't have the fraction that according to p and 1 minus p. Okay, so that's the definition. So then you can ask, okay, the joint probability of a sequence x1, x2, xn appear is, okay, for px1 it appear with this probability, x2 with this probability, etc. It's really just product because we're assuming independent and identically distributed. And we can see for a typical sequence, it appear with a probability p, right? 0 appear with probability p, and there are an average of np zeros. So let me just number of 0, okay, and number of 1 appear with probability 1 minus p, and there are n times 1 minus p of those 1. Okay, so that's the probability of each, and this appear to be just 2 raised to minus n times the Shannon entropy. So this h of x in the binary case is p log 2p minus 1 minus p log 2 minus p. Okay, and so this is where Shannon entropy appear. So this means that each appear with probability like that. So how many of them in this typical sequence is really just 2 to the n h is the number of typical sequence. Okay. Okay. So this also means that, yeah, so the number of bits, right? So from here, it's sort of intuitive that this is the average number of bits that I need to use, right? So for a sequence of n bits, I need to use n times the Shannon entropy to encode those messages in a typical sequence. For atypical sequences, then we cannot compress. But these appear rarely. So in the case that you don't want approximation, you may need to assign some specific sequence to this rare but atypical sequence. Okay. So this is the Shannon's noiseless channel coding theorem. So I don't want to prove rigorously, but I already give enough intuition. This goes beyond the binary case. So here we are assuming the binary, and we naturally leads to this. So this is the binary case of the Shannon noiseless channel coding theorem. Okay, but the exact statement of the theorem you can see in Nielsen and Trans 0.12.4. So suppose xi is an IID, so this IID is independent, identically distributed. Information source is a source with entropy rate h of x. So the theorem basically says at what rate you can compress. So we know this Shannon entropy is the key number. So if we are using a rate r that is greater than the Shannon entropy, then the compression scheme is reliable. Okay. But if you try to compress with a rate which is less than the Shannon entropy, then doesn't matter how you compress, the scheme will not be reliable. Okay, so I don't want to define rigorously reliable or unreliable. Okay, but that's the content of the theorem. Okay. So the question for us to ask is, how do we generate this to quantum regime? So in the quantum regime, the alphabet is going to be drawn from quantum states. So you may have a set of quantum state, phi x. X is just subscript to indicate which letters, for example. Okay. And it would also appear with certain probability labeled as qx. So in a sense that this source is to describe this source, you can use an ensemble of rho. So it would emit phi x with probability qx. So this is a density matrix. I'm sure by now you are familiar with this language. So, and how do we generate the typical sequence? We're going to generalize that to typical subspace, and a typical sequence will be generated to a typical subspace. Okay. So with this expectation, we could immediately write down what it should look like in a quantum case. This is actually called Schumacher theorem. Quantum data compression. Okay. Or also called quantum Shannon noiseless channel coding. It really just is a name, but it regards how much is the rate that you can reliably compress. In this case, classical information. In the latter case is the quantum information. Okay, so I'm just changing the word, but you see that this is how we generalize. So suppose we're emitting a quantum state, a source emitting quantum states. It's IID, quantum information source with entropy rate. But this entropy is replaced by, I forgot that maybe fourth here, Shannon entropy is generalized to von Neumann entropy. Okay, so it will be S, B, row, yeah. So sometimes I'll drop the V here. So the upshot of that, if we generalize this, is that if we try to use a rate meaning the number of qubit per message, per letter, yeah. So if this rate is greater than the phenomenon entropy, then there is a reliable scheme that you can compress the source, okay? If you're trying to compress with a rate less than this phenomenon entropy, then the compression will not be reliable, okay? So that's a straightforward generalization. So how do we prove this, or at least how do we understand this intuitively? So before I do that, I want to pause to see if you have any question on the generalization. So I think maybe a computer science student would probably already know this. So it's maybe not necessarily familiar with student of physics or math. Maybe applied math student may already know this. Okay.
Is there a formula for R again?
Say that again.
Is there a formula for R?
R is just any number. So you have a number, you have a entropy rate, right? So you try to, R is really just, okay, R is the number, average number of bit, right? Remember we talked about this example. This example, we talk about this. The average number of bits that we need to encode is 7/4, right?
Yeah.
So that is the R that we use. Okay, that's the rate. But you could use array which is larger. You could use more bits, which is fine. So that's the content of the theorem. If you try to use less than that, then the compression scheme will not be reliable. So R is any rate that you set. Okay. And so
how is it related to the typical and atypical discussion?
Can you speak louder?
So how is this R related to the typical and atypical case?
So the entropy is related to that. Entropy is related to the typical sequence, right? The number of typical sequence is 2 to the n times the entropy. But R is basically R is a number that you try to encode. So the question is, so if you use 2 to the n times R object to encode, and this is the number is greater than the number of typical sequences, then you can, of course, reliably encode that, right? So you have more that you can assign to, right? So that intuitively show that I can reliably encode that, even though I did not tell you how to do that. So, and this is also the case with the quantum. Okay, so R is basically the average number of qubits you need to use, right, for each letter in the alphabet. Okay, so I'm just rewriting that. Yeah, this is also the quantum version of the Shannon theorem. Okay.
Thanks.
Yeah, I should add 4. H of x is generalized to SV of rho. Okay. So to understand this, if you think in the diagonal basis of rho, then it will be straightforward. So let's just look at this. So the phi x and qx, they are not, so in general, generally not eigenstate and eigenvalues. So yeah, so this Q and phi, they are not eigenstates in general. So I'll give you example later, but so it's natural that you work in the eigenbasis. So you diagonalize. So I diagonalize rho and have some eigenvalue and eigenvector associated with that. I will use the same symbol, lambda I. So for example, if you have a qubit, you diagonalize that. There's some eigenvalue and eigenstate and some probability. So for example, it could be the zero. This quotation zero may point into any poles of the Bloch sphere, and one is the antipole of that. And P is just the eigenvalue of each of states. Yeah.
So phi of x, they are not orthogonal states, right?
So for example, let me just give an example. I just say phi x equal to 0 is 0. Phi x of 1 is plus. So,
Okay,
and
so
they
not
appear with,
necessarily.
yeah.
I see.
Let's
Thank
say
you.
we have this. This will be the example that I'm going to use. But okay. So if I diagonalize that, then I see that because the source is IID, so on average, this is like a direct product of this row and copies of row. So if you think in terms of the Shannon, the way we understand the Shannon entropy, Shannon coding theorem, we will also separate into typical sequences, and those will be composed of state. In this quantum case, states of zeros and one. In this particular basis, this diagonalized basis, eigenbasis, these would form typical sequences, right? This, and I can write a projector. So basically, if Z1, Z2, Zn are just like the 0, 1, that appear with the correct distribution, right? A fraction of p is 0 and a fraction of 1 minus p is 1. Then I define these as a typical subspace. This projector to that is a typical subspace. Okay. So I don't necessarily want to define typical sequences because these are just in this basis, but I want to define a subspace. Okay. And you can also think about that there are 2 to the n times s such sequences. Well, this is the dimension of that. Okay, that's the dimension. Maybe I should say this is the dimension of the subspace. Okay, and I can write a projector to specify projector to that subspace. Okay, so you just need to slightly extend the notion. Okay, but what that means is we can take a unitary transformation, take n qubits state phi. These phi would come from maybe emitting these states. So, but in general, because we know the subspace, we can find a unitary transformation that takes any qubit phi lambda in this typical subspace to one state that we can compress with fewer number of qubits. So I label this as a compress. So I can transform a compressed state in this typical subspace to one that has really few number of qubits. So yeah, as I label here, is basically n times the Shannon fundamental entropy. Delta is just allow you to add some small number. Okay, so you can basically forget the delta. Yeah. So you can compress to n times the entropy, number of qubit, and the rest you would transform to a fixed state 0. the 0 is a product of 0, for example. Yeah, and the number would be just m minus n s0. So just ignore the delta, okay? Okay, so basically what Alice, if there are two players involved, Alice would want to send a message to Bob. So what she will want to do is to compress this to as few as number of qubits as possible, and then it would send over to Bob. So this would save some resource than sending directly the state, right? This would may involve n qubit, but if I can save that, I could be able to send, compress and send fewer number of qubits. Okay. Okay. Yeah, so this is basically what I said. So these files could come from the source emitting. Initially, you want to emitting according to this distribution, but I don't want to directly send this file over to Bob. Instead, I want to apply U to compress. Okay. And so you see that when I compress, I desire that the last few qubits should be in 0. So what I could do is I can measure these last few qubits to see if it really projects to 0. Okay, so if the result is really 0, that means Alice successfully compresses this state that she wants to send into the typical subspace. Okay, and that could be represented by fewer number of qubits. Then she sends this to Bob, and Bob can decode this or decompress this or uncompress by really just appending a 0 to this phi compress and then apply the inverse of unitary. That should give you the phi lambda. Okay. Okay, so yeah. So, but if the result for Alice measurement is not 0, that means she does not successfully project to a compressed or a typical subspace. So that means whatever, if she send the state, that would not be useful. That would have probably not so useful. So the best thing she can do is to send a compressed state so that when Bob decompress that, this state lambda 1 would have a largest probability in a typical subspace. Okay, basically, the second case means that the procedure failed, but we want to send some state that has the largest overlap with the typical subspace. So that would somehow enhance the probability. But this state is actually not so useful in this. The only useful one is 1. Okay. Yeah, it looks, yeah.
I have a question. So if the actual state is not in the typical space, and it still can get all 0 result with a probability.
No, so that's the design. That's the design of this unitary. You transform that to this is 0, and the rest would be compressed. Yeah.
But if I give you a state that is a superposition of this good state and a bad state.
So when you measure and you get 0, then it would collapse to get the compressed one. But if you may have some probability to get let's say 1 0 0 0, then the one that get projected is not in the typical subspace. Okay, but that would happen with a fewer probability. Does that make sense? So I'm going to give you an example because this is really that would fail. That would fail. So what she?
But Alice do not know.
Alice would know because she measured.
Yeah,
0.
but I mean, if I give you a state that is not a typical state, and it still can measure all 0.
If it has some overlap with the typical subspace, then there will be some probability, but that would probably be small.
Okay, I get your idea.
Okay.
Thank you.
So I think the next example would make my statement more concrete. So in fact, this is the state that I wrote down. So this I use, for example, polarization of photons. This could be a horizontally polarized light. And this is diagonally polarized light. Okay. And they appear with probability 1/2. And we know they are not orthogonal. So H, so this would also be 0, and this is plus. Okay. H and D has overlap 1/√2. Okay, so if you want to write in terms of vectors, these are how they look like. On average, there's a density matrix, right? 1/2 mixture of H and 1/2 mixture of D. D1, this is the matrix. This is the 2x2 matrix. Okay, you can diagonalize that. So I did that here. So the eigenstates are Q and Q bar. And in fact, this is just 22.5 degree and 112.5 degree. So the vectors are these. This is really just simple, straightforward diagonalization. The eigenvalues are cosine square of pi over a and sine square of pi over a. Okay, so they add up to 1, right? The entropy, fundamental entropy of this ensemble is about 0.6. So this is log 2 basis. Okay, it's about 0.6. So what that means is, if I have measures only have three, then I can compress, because 3 times 0.6 is about 1.8. So that means I can use 2 qubit to encode a 3 qubit message. Okay. So let's see how we can do that. And we also know the typical subspace. And here we're going to choose the typical subspace. So that 4 of them, because we would want to use 2 qubits, right? So 2 qubit has 2 to the 2. So we're going to select the largest 4 eigenvalue to be in the typical subspace. The largest 4 eigenvalue are from, you can see the lambda 1 is greater than, so lambda q is greater than lambda q bar. So you want to select q, this is the largest eigenvalue or probability, okay? This is lambda q. The one that's the next one is this q bar, right? There are 3 of them. Okay. These 4 constitute the basis states of the typical subspace, and the remaining 4. So as I label 1, 2, 3, 4, these are what I wrote in the previous slide. The remaining 4 states have fewer probability or fewer eigenvalues. Okay. Okay, so so we can ask the probability in this subspace will be just the sum of these eigenvalues. So if you take the sum of these 4, it's 0.94 roughly. And the probability in the atypical subspace is 0.058. So it's quite small. That's basically the sum of the remaining 4 eigenvalues. Okay. So there's these 2 numbers already indicating that it's probably better to use the typical subspace. Okay. So then what Alice and Bob would do is that they should agree some scheme of unitary transformation that they will use to compress. Okay, so for example, you can assign maybe they transform 1. This is 3 qubit state 2 HHH, and 2 also to HVH, 3 to VHH, 4 to VVH. The idea is that I want to have the last bit to be always H, right? So H will be an indicator of the typical subspace. And this is V, so that's indicator of a typical subspace. Okay, number per. So this is indicator of typical subspace. Okay. Okay, so suppose they agree in advance the unitary that they can use to compress. So suppose Alice would send some message. So Alice could send maybe in her original, she could send this, right? She could send these. Okay, so but these can be always expanded in the different bases, right? Can be expanded in the 1, 2, 3, 4, 5, 6, 7, 8 bases. But actually what we want is we want the message to be in the typical subspace, meaning that we want the first 4 coefficient to be larger than the last 4. Okay, so what they do is for Alice to apply this unitary that we defined previously to this, right? So this is this define the unitary. Okay. So that assume Alice applied to her message, and then she would measure the third qubit. Just remind you the third qubit. If you measure the third qubit, if it's H, then you know it's in a typical subspace. If it's V, then it's not. Okay. So if H is what she obtained, she successfully projects psi into the typical subspace. She essentially project the state into this form. Okay, but this H is redundant. The third H is redundant, so she could just remove the third qubit, and then she obtained a 2-qubit compressed message. She sent this message to Bob, and Bob can uncompress by applying the inverse of unitary, and Bob would obtain this message. This message, although it's not necessarily the same as before, but it has the initial really large overlap or fidelity with the intended message psi, right? So has fidelity really just determined by the p lambda is the sum of these 4 eigenvalues, right? Okay, already computed here. That's the complement of the number. Okay. So she would be able to send this with a fidelity 0.94. Okay.
Mm.
Yes. You have a question?
So the typical space, that is the product of density matrix. So does it contain entanglement state, or it only contain direct product state?
Yeah, so the bases are not entangled, but if you mix 1, 2, 3, 4, then it's entangled. So, but in this particular expression, it can be entangled among the first 2 qubits. Remember our concurrence is A1 times A4 minus A2 times A3 is non-zero, then this compressed state is entangled.
So even the source emits some entangled state, we can still compress it.
Yes, yeah.
Thank you.
Yeah, but in this particular case, if Alice is only emitting HDH, then it's not entangled. But I think I should take back that a little bit. I'm assuming Alice is source is emitting like this, and that occur with some probability distribution according to the ensemble. If the state, entangled state that Alice is emitting on average satisfy this. So if the reduced density matrix by tracing over the other satisfy this, then the compression will still hold. Okay. So you cannot send arbitrary entangled state, but the reduced density matrix need to obey with the ensemble, the rho. Okay, that's the requirement. Okay.
Can you repeat? I do not follow.
So I'm saying that everything that determines the rate is the fundamental entropy of rho. Rho is the average, so the ensemble of your source.
Yeah.
Ensemble discretion of the source.
Of a single qubit.
For a single qubit, yeah. So if your entangled state on average trace out any of the remaining qubit, the rest of one single qubit has the same ensemble discretion, then it should work.
Oh, okay.
Yeah, but you cannot say arbitrary entangled state that does not satisfy that. Okay. So we say that Alice measure this applying this U and measure the third qubit. If it's H, then she's successfully obtaining the compressed state. She can use this, send it to Bob. Bob decompress by appending the H to the 2-qubit state, applying the inverse of U, would obtain this. This has high fidelity with the beginning of psi because this psi is in the typical subspace. So the first 4 coefficients should be larger than the last 4. And that's the fidelity, 0.94. Okay. But if the result is V, she fails to project her state into the typical subspace. So the best thing she can do is to send the HH, because HH appended with this H, when you invert that, you get state 1. State 1 is the one that has the highest probability in the typical subspace if you use Alice source. Okay, so the best thing she can do is to send HH to Bob. Then Bob would decompose to this and has the fidelity with the initial state of this value. So this is 0.0581 is this here, and the last factor is the fidelity 1 with the HH. Okay, that's square. Okay, so this is basically average fidelity. So you see that when it's successful, this has 95, almost 95% fidelity. You say, okay, is this really useful? So you can compare if we don't do any compression, but we are only limited to send still 2 qubits. In this case, what can Alice do? Alice will probably send the first 2 qubits, and then just ask Bob to guess the third letter. Okay, so we're saying that DH, for example, if you have some message, is 3 qubit. The best what Alice can do is just send the first 2 and then ask Bob to guess, because you cannot you cannot compress, and the only thing you need to do is to have some guessing game. So suppose Bob have to guess the third letter. Machine, he knows that, well, if I use H or use D, it's actually not the best because I may succeed in one case, fail the other, but probably the best guess is to use Q because Q is the largest eigenvectors of rho. Okay. Rho, yeah. Q is the largest eigenvector of rho. And then that would have fidelity with H or D only 85%, which is less than 94. Okay. But you could also try to think maybe Alice and Bob could do something different. But it's roughly just this. So there is at least some advantage, 95% versus 85. Maybe about 10% fidelity increase if they use compression. Okay. Any questions?
Yeah. So do you mean that if it is failed, HH is better than the original two qubits?
In this case.
Yeah. So
because yeah, because when Bob attach the H and do the inversion, right, this will be mapped to 1, right?
yeah.
1 is the one that has the largest eigenvalues, right? This or probability. The probability is the cosine square cube. So remember, this is lambda q is cosine square.
Yeah.
Then if you have 3q that appear with probability cosine to the 6.
So for example, if I give you 8,
just give me this.
Yeah, then you'll get
that would have the overlap with the state that you send in really just less low. This
I
is
mean,
a small number.
If I'll give you 8, you still send Bob HH.
Oh, if you want to send A to Bob, is that what you're trying to say?
Yeah, if I emit 8 to you and you do the measurement and fail.
So if you are always send me A, of course I would fail a lot. But this sending me the 8 is not a typical, it's not, you will not obey the density matrix, right? If you always send me 8, reduced density matrix is Q bar. This is not in this. So whatever Alice send need to be come from, initially, needs to come from, draw from this ensemble, okay? Yeah, so you should talk about the average of the message.
My question,
of course, I can send you, in the previous Shannon case, I can always send you really 1, 1, 1, 1, which, but then on average, you are sending me, if you always send me 1, 1, 1, 1, if I don't know what you're sending, maybe I will not be able to compress, but if I know you are sending 1, 1, 1, I could just tell the other party that you are always sending that. But what I'm saying is that the source need to emit the bit or qubit with some distribution, right? That's the assumption. And the source is emitting quantum state according to this distribution. If you are sending me something else, then I would use a different encoding scheme, right? If you are sending me a different distribution, then I'm using
the next slide.
Yeah.
Yeah, this is slide. So yeah, I don't understand the 2. You mean that y is 0 prime?
2 is not so important because it's already not in the typical subspace.
Yeah.
Whatever you do here does not much.
Yeah. So she can
remedy the situation. Whatever
back.
she does here is just trying to raise the fidelity a little bit. By a little bit, you can see the example, right, in here.
So my question is, why 0 prime has the better fidelity than 5 prime?
0 prime.
Yeah, because 5 prime is the first 2 qubits you did not measure. So you still send the first 2 qubits to Bob.
No, so this is when she measure and get B,
she still have 2 qubits.
She would be in this, she has projected her state into the second group.
Yeah.
Right, the second group.
Yeah.
The second group here. But you know the state that she sent in has high fidelity, so high weight in the first 4 states.
Yeah.
Right, so typically on average, this would have.
I see, because the 8 groups are orthogonal.
Yes, yeah, but the point is not orthogonal. The point is typically the weight in the first 4 are larger than the last 4. So on average, it's better you send a state that has a highest weight as possible. Of course, for a particular example, you may fail, but on average, you will gain a little bit fidelity. I mean, you could do the calculation using other number, but this would be smaller than this. But adding this, as I said, this is so small that you can just ignore, right? 0.036 adding to 0.94 doesn't get much. So you can just ignore, you can say, okay, I fail, let's try again. Right? You can just, what she can do is she encode the message again, and then she will have high probability of getting the H. Okay. But if she has to just using one copy to send, then she will just send this one. Okay. Okay, so yeah, so that's the end of the quantum data compression, but I want to bring this back to the content when we talk about entanglement cost and entanglement formation. So remember we were trying to dilute, maybe I'm just writing 5+, I want to dilute to get many psi, right? So psi is a 2-qubit entangled state, cosine 0 plus sine 1. So how do I achieve that? Because we mentioned that it's reversible in the asymptotic limit. So how do they achieve that? So what they could do is, so the starting point is they share k pairs of maximally entangled state, failed state. Okay. But they want to actually establish n pair of psi, and n is greater than k. So you may say, oh, it's not possible because you want to create more qubits. But they could do that because Alice could locally prepare n pairs of psi, right? And she compressed because the reduced density matrix will be, if you trace over that, so rho A will be cosine square 0 plus sine square 1. So as long as the entropy is not 1, so as long as the S is not 1, she can win by compressing, right? So she can just compress the blue part, right? So each entangles, this is locally created, but she compressed this one. They basically compressed all together by using the scheme that we mentioned earlier, right? So just using the data compression, and she can send k qubits using the teleportation, okay? And that would appear in the Bob side, and Bob just decompress. So that should recover that. So initially, this is local, but after the scheme, the entanglement will be shared across, and you have n copy of psi. Okay. So I think this complete the entanglement cause, or this is the entanglement. The process is the dilution, but the cause, entanglement cause, is really the ratio of k over n. Okay. I hope that makes sense now. So the entanglement, dilution, distillation, that sort of makes sense. And how you understand that the two processes are reversible if the number n goes to infinity. Okay. Any questions? So I plan to cover this week's new topic. So, but I don't think I would have enough time to do that. But I mean, just give you a review what I'm going to do. So I'm going to talk about no cloning. So no cloning of quantum states. Yeah. So I'm going to go about no cloning, and then ask the question: if you have non-orthogonal states, how do we distinguish them? So how do we know which one is psi 1, which one is psi 2? And what is the probability of success? And things like that. Then I would talk about how do you measure and know what the source is emitting. So a source is emitting a state. How do I characterize? So by measurement and know rho. So I estimate rho. This is called tomography, but you could also ask a process. So if I have rho and send in, it give me some process acting on rho. So how do I infer this process? And then I would also talk about one important subject in quantum cryptography, which is the key distribution. By sending non-orthogonal state, which we would have talked about there, sending 0 plus to encode maybe 0 and 1 minus to encode 1. So there's some way to establish some secret key, which you can use for communication, secure communication. Okay, so that's basically a maybe 2 minutes quick overview of what I'm going to talk about on Wednesday. So I don't think I'll have time to go through the detail, but let me stop here to see if you have any further questions.
So is our ability to do data compression really a manifestation of the monogamy of entanglement property amongst qubits?
I see that there's not much relation with the monogamy.
Okay. Yeah, because I was just wondering.
You could also, right? So it really depends on just the reduced density matrix of the source that's emitting. So when you trace over one of the particles that you are not sending, this is in this ensemble. So it could be that this guy that you were trying to send has some entanglement with some complicated entanglement with the rest. Okay. And as long as the trace, the reduced density matrix is not a completely mixed state, then you can compress. Yeah. And in a large number n limit, this compression can be made very high fidelity. That will approach to the Schumacher's limit. Okay, so it does not relate that much to the monogamy of entanglement.
Yeah, but if there's no monogamy of entanglement, that means we could for multiple qubits, we could have the same amount of entanglement as maybe or more than what 2 qubits can have. Then the kind of compression wouldn't work. That's what I was thinking. But
so it could be that this state reduced to a completely mixed state. That is because it's entangled with other. So of course there's some limitation of how many particles can entangle with one another, but the fact that that this can be compressed, it really depends on the reduced density matrix. So it could happen that it cannot be compressed further because it's already a completely mixed state, and it may come from the entanglement. Okay.
I see. Thank you.
Okay, sure. Any more questions? Okay, if not, let's end the lecture here and see you Wednesday.
Thank you. Bye-bye.
Thanks.